just to recap for the recording, exam scores were low. They're not where I wanted them to be. So it means that you guys need to study a little bit more, specifically the single cycle data path. You struggled with it on the homework and on the exam. And pipelining the data path plus the performance equations with pipelining. So to help you get started with reviewing this for the future, because exam 3 does build on the knowledge of exam 1 and 2. It's not cumulative, but in the sense of you need the prerequisite knowledge in order to understand the new concepts. So to help you get started with reviewing the concepts and to also solve this problem of the exam scores were a little bit too low, we're offering these exam 2 corrections. So for your exam 2 corrections, you will either print out your exam or you can come and get your exam from me. I have them all in my office. You just have to come and see me to get it. And then you have access to your scanned exam from Gradescope. And the next thing you're going to do is just mark where your answer was wrong. So there is some notes on Gradescope about why your answer was wrong. And then in the left margin next to the question number, you need to put how many points you were marked off for the whole question. You can get that directly from Gradescope. And how many points you received back with your corrections. And your corrections will give you half points back. So if I miss 10 points on a question, I'll get 5 points back. Assuming that you meet all of this criteria. So these two things need to be clearly marked. Put a minus for the points missed, a plus for the points back. And then on a separate sheet of paper, you need to do the following things. You need to send it correctly. So this is your correction. Okay. And then you need an explanation of why your answer was wrong on the exam. This needs to be more than I didn't know what I was doing on the exam. You need to clearly state what went wrong. And then to receive any credits, you must make corrections for the entire question. You cannot just do part A or part B. The only reason that you would only do one part is if you only missed points on that one part. Because for you, that is the entirety of the question, okay? So you need to submit all of this to Gradescope before the due date, which is going to be, I believe this is next Monday, before class. So you have a week to do this. And when you submit to Gradescope, you must select the pages that correspond to each question. And your original exam answer should be first, and then your correction when you're selecting the pages. And if you don't follow any one of these instructions, you will just not receive any credit. It has to be following all of this exactly. If you don't have an explanation, but you did the correction, you're not getting points back. If you are missing how many points you missed, plus how many points you are expecting back, with half points being received back, you will not receive any credit back. Okay. So this was exam 2 correction. The other thing is homework 4, homework 5, and homework 6 are all released on Canvas. You can complete homework 4 right now. You can almost complete homework 5 right now after today. and all of the due dates are listed. One thing that I have to adjust are due dates for reading because this Friday is the observance of Veterans Day. So there was originally a reading due this Friday, but it's gonna be due Monday, so everything is gonna be pushed back by one session. Okay, but the key things are, from grading your guys' homework and exams, you need to understand the single cycle data path. You need to understand the pipeline data path. You need to understand the difference between performance in single cycle versus pipeline. Many of you guys did do well on the exam. It had very high standard deviation. The standard deviation was 10. So many of you guys did do very well on the exam, but others did poorly on the exam. So if you are not at the grade that you want to be at, do review these concepts because they are important to build upon for not just this lecture, but all the future lectures, right? If you don't understand pipelining, this lecture is going to be hard for you to understand. You need to review, okay? And the other thing I want to say is I offer these corrections every now and then, but do not expect them every single time, right? So just like how the first exam you guys did well, I did not offer these exam corrections, right? Okay, so are you guys done filling out the sheet yet? Do you need more time? Questions?
For the electives, do we need specifics or can we just write when we plan to take each one?
What do you mean?
Because it's just blank on our page. So do you want us to write the electives we want to take on that?
Oh,
page?
yeah. Yeah. So for the blank electives, do put what you plan on taking.
Okay.
All right, so I think we can just maybe, yes, Chris.
For the classes that we're currently taking.
Yeah, so any class that you have taken or you're currently enrolled in has a check mark. Okay. So maybe you guys can fill out this sheet while I continue the lecture, since we were okay with multitasking. Yes or no? All right, so we have covered pipelining. We've covered why it's an improvement over a single cycle. We've covered the pipeline data path. We've covered pipeline control. And then we're on hazards and dependencies. We've covered structural hazards. We've finished data hazards. Today, we're going to cover control hazards. And we have a little bit of extra review on data hazards before we go to control hazards. So with data hazards, we saw that stalls reduce performance, right? Every time that you stall once, it's like you're adding an extra instruction. It does nothing. But these stalls are required to get correct results. So one thing that we can do, along with our on-the-fly detection, we can also have the compiler rearrange code to avoid hazards and stalls. And this just requires that the compiler knows and has some knowledge of the pipeline structure. So for us, in our five-stage pipeline, when we have R-type dependencies, do we require any stalls? R-type dependency. Yeah, there's no stalls, right? It's available after execute. The earliest any instruction needs it is in execute. Currently, there is one instruction that we will cover that needs it in decode. But for now, with our current knowledge, we have no stalls. Okay? So the compiler would not have to rearrange any archetype dependencies. Right? But when we have load word, and there's a dependent instruction right after, we require how many stalls? One stall. Okay? Because it's available after memory, which is one stage after execute. So if the compiler knows about this, right, it can detect that there's a dependency, and it can try and rearrange the code such that it finds an independent instruction to put in between the load word and the dependent instruction of the load word. And then by putting that independent instruction in between, it's like we've stalled, but we're actually doing something useful in the meantime, right? So here is our code scheduling. So if we have this code, it's going to implement this code. It's going to add these two array positions, put them here, add these two array positions, put them here. We have these hazards, load word, add, load word, add, right? And overall, this would take 13 cycles because we have 1, 2 stalls. But if we rearrange the code, and this code is still executing the exact same code up here as this code on the left, but now there's no data hazard that can't be forwarded immediately, right? So this load word is still going to be a dependency for this add, but we shove the other load word in between. And this load word is not dependent on this load word, right? So this is like having a stall, but we're doing this useful instruction of a load word. And then because we have these two instructions in between this load word and its dependent instruction, we again don't need to stall. So if the compiler has some information about if there's this dependency with this type of instruction, it requires this amount of stalls, maybe it can find some independent instructions, just reorder the code, it's the exact same results, but now there's no stalling in hardware. But if it's not possible, we still have stalling in hardware available, right? And this is something that we've talked about quite a bit before, right? We always say, load in some stuff, do your operation, store the results. We don't want to load, operate, okay? And we'll see more why that is important in the next chapter of memory. So here is another example. So considering the following MIPS code segments, we have store word, add, load word, and do we have a requirement to stall with this current version of code? Nodding heads. We all in agreement though? Yes or no?
We could move load word up.
Okay, so the first question is just, is there a requirement to stall? And you're saying that load word has, right?
Yes.
Because T1, right? So the question is now with code scheduling, like you're saying, you want to move load word up. Where can I move load word up?
Add, put the load,
In between store and add? So we can't do that because this add is reading from T1, right? And this load word is going to write to T1. So this is supposed to be the previous value of T1, but if the load word is in front of it, now it's the new value from load word. So what's something else that we can do?
You can take the store word
down.
and put it between the low word and the and.
Yes. So this store word is independent. Right? And if we move it from here to here, we have the same resulting code. It's still going to give us the same correct results, but now we don't have a stall. Okay? So then we can also ask these questions. How many cycles are currently required? What is the answer to this? 9. Okay, so 1, 2, 3, 4, plus 4, plus 1 stall, right? So 9, right? What is the ALU doing in cycle 4?
Forming the add execute.
So 1, 2, 3, and then this is in executes, this is in decode, and then 4. This one is in execute, right? And there's no stalls between these two in its current version, right? So it is adding T1 and T4. All right, so this was your question, but we already went over this. So this was, in this current form, it's 9. But after we move the store word to in between here, what is our total number going to be? Yeah, it's going to be reduced by 1, okay? Because we no longer have to solve. And then we already talked about this. It's adding T1 and T4. All right. So this is similar to a question on your homework, right? We suppose that executes is the longest time in the pipeline stage. To reduce the cycle time, we're going to split it in half. The pipeline is going to become fetch, decode, execute 1, execute 2, memory, and write back. And we're going to assume the input data must be available at the start of execute 1, and the ALU output is not available until after execute 2. Now, how many hardware stalls are required for the following code? We have load word, and then an immediate dependent add. So since we didn't do the other 2 questions, maybe this can be your poll question. And your code for today is 595. Let's do A is 0, B is 1, C is 2, D is 3, E is 1. We have this code, we have this new pipeline architecture. How many stalls are required?
What's the code again?
595. We'll check. 595, yeah.
You said A is 0.
A is 0, B is 1, C is 2. Yeah, I don't see answers changing. Are we still thinking about this? Alright. So we are not close to the threshold. So do talk to the people around you. Maybe draw the multi-cycle diagram of this. Maybe the visual will be helpful to see how many cycles are required.
Interesting. I guess there's maybe this too because it's a long video in the negative state. But for now, I'm doing it. Because we can execute one because the template for once available. You know. Just solves with that 6 stage by games. Here's just like to take something some right step down now, but it like my CS life will be for summer semester. Schedule doesn't allow. Let's get this thing, because that might be with 43.6 should be. I see. So. Don't you guys would think you're there?
I don't hear much more discussion on this. You change your answer if you were. Let's change your answer. Okay, so we did have movements, but not enough towards the right answer. So the right answer in this case, as we will talk about in just a moment, is C, which was going to be 2. You don't need to change your answer to it now. It doesn't matter. Remember, this is just, you need to participate. It's not based on correctness. But let's just start with, from the code, do we even have a problem? Yes. The problem is between R1, right? So now, to help us answer this question, I'm going to draw this multi-cycle diagram. I'm just going to say that this first one, that's already written out for me. That's for the load word, right? And now the second, I'm going to, so in cycle 2, I'm going to fetch the app, right? In cycle 3, the load word starts its execute, and I can decode the app. And it's in the decode stage. I have my hazard detection unit, right? The hazard detection unit says, I'm trying to read from register 1. The instruction in front of me is operating and storing to register 1, and it's a load word because it's reading from memory. So I need to stop. So in order to stall, I just redo decode, right? We indicate that it's stall with this cloud thing. Okay,
Is that the first stall or the second stall?
this is the first stall, because this is the first time I'm redoing decode. Right? And now we're in decode again. The instruction in front of us, it still doesn't have its result, right? So the hazard detection unit would say, stall again, right? We don't have our result because we don't have the result until after memory for load word. So decode, there's our stall. This is our second stall. And now when we do this, we can see that the load word is in memory. It will have its results in the next cycle. And we can forward it. So we're allowed to go to execute. The instruction behind us can now go into decode. We would indicate this forward with an arrow, right? So this is indeed to, just as a recap. And so I don't write on this. Pipelining is improving performance by increasing instruction throughputs, right? And we increase instruction throughputs by executing multiple instructions in parallel. In a 5-stage pipeline, when we're fully utilized, how many instructions are we working on at the same time?
Stages.
So in 5-stage pipeline, that is 5 instructions. And we're fully utilized. We are not always going to be fully utilized, but that is the goal, right? But this is subject to hazards that prevent starting the next instruction in the next cycle, right? Structural hazards. We talked about how this would occur. But for our simple pipeline, this does not occur, right? We talked about data hazards and we just finished the last of data hazards. You need to wait for previous instruction to complete its read register. And now we're going to talk about control hazards. And control hazards are our branches. So our current design for branch instructions, the decision that the branch is going to be taken or not taken occurs in the memory stage, right? Because we do the subtract in the executes, that gives us the 0 flag, and then in the memory stage, we update P. So this means that we don't know what the next instruction is until 4 cycles into the branch instruction, right? So one thing that we can do is just wait until the branch is done, right? Don't fetch anything. So this would mean that we would stall 3 cycles, right? So we could do this, right? So here we have a branch. We fetched it. We figure out, oh, this is a branch. Don't fetch the next instruction, just stall. And then when the branch is resolved in memory, okay, now we've updated PP. Now you can fetch the next correct instruction. Right, so we have 1, 2, 3 stalls. So do we like this approach? Right, basically this means that branch instructions are equivalent to 4 instructions. We don't like this out, right? So what can we do about it?
We can assume whether a branch goes through or not and act like that until we get to memory.
So we can do some prediction, right? And one other reason that we don't like this is that, like we talked about, the 5-stage pipeline, simplified. Real pipelines are longer than 20 stages. Okay, so if your branch is decided this late So if it's 20 stages, the equivalent would be like stage 15. You're stalling for 14 cycles. That's not acceptable, right? So the other reason is branches are usually around 10 to 20% of your total instruction. So it would be a huge performance impact. So this is unacceptable. So these control hazards are arising because we must fetch the next instruction before we know if we're branching or where we are branching. So these control hazards can be detected in hardware, right? Once we're in the decode stage, we have the opcode. We know what the opcode means. We know if it's a branch. We know if it's a jump. We know all of these things, right? So there are many different ways that we can reduce the impact of these control hazards. The first is what we talked about with branch prediction. We'll talk about this in detail. We can reduce the delay or cost of the branch hazards by trying to figure out if we are going to branch earlier. We don't need to wait until memory to figure this out. We have everything we need after we read the registers, right? And we read the registers in which stage?
We would have everything for execute, but we would get it after the decode.
Yeah, we have everything in decode. So we can resolve our branch and decode. If we resolve our branch and decode, then rather than costing us 3 cycles, now it only costs us 1 cycle. And the other thing we can do is code scheduling. So code scheduling, if the compiler knows that when I have a branch, I have this requirement of 3 cycles of stalling. Can I find 3 independent instructions of this branch and execute those while we wait for the branch to resolve? This is very difficult to find 3 independent instructions. And again, like we talked about with deeper pipelines, no way you're finding 15 independent instructions. It's not going to be possible. And the other thing is dynamic branch prediction. So this goes again back to what you were saying. Maybe rather than always guessing that it's not going to be taken or always guessing it's going to be taken, we can dynamically predict based on the branch history. Like if the branch has been taken the last 2 times, perhaps next time it will be taken again, right? So solution 1, static branch prediction. We are just going to predict the outcome of the branch to be not taken every single time. So we're going to fetch the instruction that is right after the branch with no delay. And if we're right, then we've started the execution of the correct instructions. We're all happy, right? Nothing is wrong. We have no performance impact. But if our prediction is wrong, then those 3 instructions that we fetched, they're not the right instructions. We need to remove them from our pipeline and make sure that they don't edit our registers or memory. So to do that, we just flush them. And we've seen what this can look like. You just set all of the control signals to 0, then they won't do anything. They can just flow through the pipeline. But it is the same result of if you didn't predict anything, right? It's like you stalled 3 times. So when we're right, we have better performance. When we're wrong, it's the same as doing nothing. And we just need to add hardware to flush the instructions if the prediction is wrong. So here is our static prediction. So here we have our branch. And we're predicting that it's not going to be taken. And we fetch this and, this or, this at. And in cycle 4, we figure out, oh, our branch was not taken. So these 3 instructions that we fetched already and are already being executed, they're correct. There's no need to do anything. So continue on as normal, right? But if we are wrong, these 3 instructions are wrong, right? We should not finish executing them. They've done no harm so far, right? I'm in executes. This one's in decode. This one's being fetched. They have not written to the register file. They have not written to memory. They have not changed our results, right? So we can just flush them. Flush them, set their control signals to 0. So when they go into memory, they don't write to memory if it was a load word. I mean a store word. If they go into write back, they don't write to the register file. If it's R type or load word or things like that. And then I can correctly fetch the branch instruction. So flush them, change the original control values to 0. And then it turns these 3 instructions into no hops, right? So the second solution is reducing the cost of the branching hazard. So we can reduce this cost by moving the decision to earlier stages. So if we move our branching decision from memory to the execute stage, we save how many cycles per branch? Currently, we need to stall 3. If we move it up from memory to execute, how many do we need to stall? 2. So we save 1. If we move it to the decode stage, we save 2. Right? So, like we talked about, when I read the registers from the decode stage, I have all the information I need to decide if we need to branch or not, right? We either branch if they're equal or branch if they're not equal based on the instruction. Right? We just need to check if those registers are equal or not. And we also have the PC plus 4 plus from the instruction, we have the offset address from the immediate. So we have everything that we need. We just need to add more hardware to check the registers and calculate the target address earlier than in the execute or memory stage. So what do we need? We need an adder to calculate the branch target address, right? And we need a comparator to compare the bits. So you can do XOR, right? XOR, if they're the same, the result is 0. If they're different, the result is 1. So you can use that and with a very large OR gate, very large AND gates to determine were these exactly the same or not, right? So we also need to copy some forwarding and hazard detection hardware. And this is what I was talking about before. If we had R-type, we never had to stall, right? R-type dependency. But now if we have a branch that's dependent on this R-type, when do we need the results of the R-type if we're resolving in decode? For the branch, if we resolve in decode, we need the information in decode, right? But if we have this set up, an R-type, and then immediately the branch, when the branch is in decode, the R-type instruction is in execute. So we don't have the result yet. So we need to stop, right? Okay, so we do, this is just showing that we need to solve. So here we have the add and the branch is dependence on the add, right? So when we're in decode, we see the instruction ahead of us is still not done finishing its results that we need. So we redo decode and then we forward from execute to decode. So this is our stall. Right? And then we can see that the same thing happens here with the load word. Right? All right, so this is our data path with branch prediction. So we just updated the hazard detection unit. And we also have updated the forwarding units to be able to forward from not just to executes, but it needs to be able to forward up here to our branch. And we've added this adder up here that takes the sign extended, shift left, immediates, and PC plus 4. And that goes into this mux to update PC. So we're no longer waiting until our decision here, and then at the beginning of memory to updates, we're at the end of decode updating PC. Okay. So we already talked about this data hazard. So if we have a load word and the branch is right after, we need to stall twice. So for one thing, there's no additional reading. We're going to use control hazards. Do please give me your filled out form so that I can get up to the ABET document. So here's your, we're reading all the numbers.
Where?
Please separate computer science and software engineering.